Alright, so this is the fourth part of systems of linear equations, which is the first part of linear algebra. And this time we're looking into... Hold on, I have it somewhere here. Yeah, there we go. Inverses and algebraic properties of matrices. So this is an extension of the last video. And so basically, like we've done like the start of matrices, so we're just continuing from there. And so these are a few properties, like a few laws of matrix arithmetic, right? A plus, yeah, see, it's the same, A plus B, B plus A. And it's called the commutative law for matrix addition. You have A plus B plus C, you can put a bracket anywhere, it'll be the same. So that's the associative law for matrix addition. Same thing if you multiply them. If you have A, B, C, you can put the bracket anywhere. You could do A open bracket B times C close bracket, or open bracket A times B close bracket C. It's still the same. That's the associative law for matrix multiplication. But that does not mean you can do BAC. It's always ABC, ABC, regardless of the bracket. It's always ABC. All right. And then here, this is the left distributive law. And so this is where I get into that thing where it's like you have to have the order right. Because if you have A, open bracket, B plus C, close bracket, when you expand it, the A always has to be to the left. So that's AB plus AC, not BA, AB, all right? And same thing with the right. If the A is on the right, then it's BA plus CA, all right? Because matrices are non-commutative. That means AB does not equal to BA because of the way you do the matrix, right? If you have, shoot, I don't have my iPad. Where is my, I have a mechanical pencil somewhere. Okay. If you have, this is not a mechanical pencil. If you have A, which is 2 by 3, and you have B, which is 3 by 2, you can do AB, and that will give you an array that has an order of 2 by 2, right? So this is AB. But if you do it the other way around and you do BA, then you get an array that has a power of 3 by 3, right? This would be BA. And as you can see, this is that has a power of 3 by 3. This has a power of 2 by 2. Therefore, they can't be the same. AB and BA are not the same, which is what gives place to these rules. And this is just a really and this is like, if you multiply them by a constant, you can like fit in the constant anywhere. It doesn't matter so long as the B and the C are in the right order. You can even have the constant like multiplying the C, like multiplying just the B. So it looks a bit weird standing here, but basically this matrix and this matrix does not swap. So that's that, and it's good to remember the names of the laws so that you really get it. But yeah, moving on, there are zero matrices, and this is like zero for a matrix. It's just a matrix of zeros. It legit looks something like this. So like 0, 0, 0, 0. And this is just, I'll just do this to prove it. It can be like any kind of shape. It can even be just like one cell, That's a zero matrix. So as long as the matrix is just a bunch of zeros, it is a zero matrix. So all the elements are zero. It's denoted as a zero. Unless the size is important, then you can do like 0 mxn. So this, ignoring this thing, you could say this is like a 0, what's that? 2 rows, 3 columns. So, oh my god, 0, 2 by 3. So if the size of the matrix is important, then you write it like that. But if not, then you can just denote this as just like 0, right? Now this acts similar to 0, like the scalar 0 that we're used to in real numbers, but it's not exactly the same, because this is something that you can do with real numbers that doesn't really work with matrices. So for example, in real numbers, if you have AB equals to AC, you can cancel out when A isn't 0, you can cancel them out and get B equals to C. That doesn't work in matrices. Same thing here. If AB equals to 0, then one of these values have to be 0, right? Either A has to be 0 or B has to be 0 if the product is 0. That's not true with matrices, all right? And I'll show that here. Let's work through this together. we have A is 0, 1, 0, 2, B is 1, 1, 3, 4, C, why, oh yeah, there's a C. Which one am I proving? Oh, I'm proving the first one, alright? I'm proving this, alright? So I'm gonna show like these are three different, you can see the numbers, they are three distinct matrices, but they will add up to the same thing. So let's work on that right now. So let's try A times B, right? A times B will be, remember it takes, so this is what, AB1, 1, AB, shoot, I think it's 2, 1, AB1, 2, and AB2, 2, right? So this is the first one, the I is the row, and the second one is the column. Yeah. So this is equal to the row, so 0, 1, and 1, 3, right? 0 times 1 is 0, 1 times 3 is 3. 1, 2, alright? So that's 1, that's 2 here. So 0 times 1 is 0, 4. Let me just try to do this off the top of my head, because there we go. So that's 3, 4, 6, 8, right? That matches. So now we know AB matches this. Let's do AC. I'm not gonna write the whole thing again. Let's just pretend all the BC are C's. It's the same thing. And then this, so that would start with a 3. And then you would have this, that would be a 4. And then you have this, that would be a 6. Then you have this, that'll be an 8. And see, these two are the same. Bam, right? So even though this is the same, and there's these two A's here, you can't cancel them out and be like, oh, B equals to C, because they clearly aren't here. And one reason behind that, you might be wondering, like, why is that a thing? It's because of, shoot, I just scribbled all over my notes. Because of these zeros, right? See here, like, the 1, 2 is the only thing that shows up, and like the 3, 4 matches between B and C. But since these two are 0, it doesn't affect like the top row of B or the top row of C. Alright, so this is like a blind spot. There's like technical terminology for that, but it's boring. And I haven't learned it through the textbook yet. It was just like extra for me to like fully understand how that works. But yeah, that's that. So moving on, we should test this as well, right? Where if like, why isn't this true? Like if AB equals 0, why isn't one of them 0 as well? But I have that here. Is this the right? This is the wrong freaking page. Hold up. Okay, here we go. So let's test that here. If we have A equals 0, 0, 1, 2 and B equals 3, 7, 0, 0, it says here it'll be 0, 0. All right. Now you can see a few similarities to here in this blind spot, right? I take my pencil. This was a blind spot. This means that none of this stuff was looked at, right? But you know, if you look at it again, these two things that we saw, the 1, 2, always interacted with like the bottom row, right? So now the bottom row in this is also 0, 0. That's just the blind spot again. So if I do try to solve it, you know, it's gonna be 0 times 3, 1 times 0. It's gonna be 0 times 7, 2 times 0. It's gonna be like everything's gonna result in 0, and you can double check that, but it just turns into 0. All right. So even though neither of these two are 0, the product is 0. Right. So there's some things that are a bit funny with matrices. So let's move on. After the 0 equivalent of a matrix, we want to look at the equivalent of the number 1 in matrices. All right. And that's what identity matrices are. All right. They're just the one. So anyway, sorry, that was a reference to like some song. Anyways, identity matrices, these are square, they have to be square. So unlike this, which is just wibbly wobbly, this has to be square, where every value is either a 0, where every value is a 0, and every value on the main diagonal is a 1, right? It's denoted with I, but you can also do IN for it because it's square. So you don't have to do like I 2 by 2 because it's always it has to be a square, right? It always has to be the same. That's why you just do like I 2. You know, you can go crazy. You can do like an I7 that's pretty big, right? So there's a few examples here. You know, I denotes either this or this. You know, this small identity matrix where it's just a 1, or this one where it's a 4 by 4 and the diagonal is all 1. Or you can do it more specifically by doing I1 or I4. That is the identity matrix, right? And, you know, why this is equivalent to 1 is if you have A, which is just a random matrix, in the order m times n, you can have A, put the I here with the size n, it'll just go back to A, or the m, it'll always go back to A. Now, just for clarification, this like n and m is just like everything keeps the same shape because when you multiply things, it has to have like the right row and column, so that smushes together. But yeah, this basically like shows, right, that like, you know, this is why we call it an identity matrix. So it has the properties of the one that we normally have in our constants, the constants that we constantly use. All right. So that's pretty simple, and we're gonna, you know, we haven't gone to any of the functionality of identity matrices, but we'll definitely come across them as we go through like the more complicated stuff. So moving on, we have inverse matrices. So an inverse matrix is something where you have a matrix A and you have its inverse. So A multiplied by its inverse is the same thing as the inverse multiplied by A, which is equal to the identity matrix. See, that's where it's used, right? This is where identity matrices are used. How does, yeah, basically it's like if you have the number 2, right? The inverse of 2 is 1 over 2. So you multiply them together, you get 1. That's how it works in like constant math, and like math in real numbers. And that's how it's used in matrices. That's what the I and the inverse matrix is for as well. But unlike real number math, not every matrix has an inverse, right? Also, they have to be a square matrix for them to even have a chance of getting an inverse. So I'm going to show you here. So B here is the inverse of A. So if I multiply it together, it's going to give I, right? So we have this, we have this. Let me just do the freaking thing so it's easier for me to kind of get where I have to go. All right, so let's multiply together. So if I do AB, right, there'll be shbing shabong. That's 2 times 3 equals 6. 5 times negative, wait, I think I'm doing it wrong. 5, it's the same thing. 1 times negative 5, that's minus 5, right? And then I move to this, so that's 2 times 5, that's 10, minus 10. Go to the other side, that is minus 3 plus 3. Go to the other side, that is minus 5 plus 6. And as you can see, that just turns into 1. Let's try to do the other way around now. Let's do BA. So, you know, we're switching these around. So we're doing the rows from B and the columns of A, right? So that should give 6 minus 5. That should give minus 15 plus 15. That should give, this should give 2 minus 2, and the last one is minus 5 plus 6. So yeah, either way we do it, the answer is 1001. Bam. So let me go, that's not the next page. What the heck is that? So yeah, those are inverse matrices. And here we can see, I want to show you something where it says here a matrix with no inverse is a singular matrix, and I can show that we can't have a matrix for this, and it's because of these three zeros here, right? And so let's pretend like the inverse of A, as we're trying to find it, let's say that's B, right? Just as a temporary thing to make it clearer. So if we want that to be true, then AB has to be equal to BA has to be equal to the identity matrix. So B will be in the same shape. B will be like it will be like a 3 by 3 matrix, right? We can use something I talked about last time, which is partitioning matrices, and split B into just like 3 columns, right? Three vectors, right? And so if we try to put that together, right, A times B as 3 vectors, right? So let's do like B1, B2, and B3. So there's a column of 3 vectors now, right? As we try to multiply this, wait, and then we have to do like, okay, wait, B1, B2, B3, blah, blah, A. If we try to solve this, what you'll notice is that with one of these, the A is gonna have to multiply with like a full row of zeros, right? And that means like in the corresponding result, one of the rows or columns is gonna just be completely like all zero, right? But that you can't have that for an identity matrix. An identity matrix has to have that one, it has to be 1, 1, 1. It has to be in this very specific shape, right? This is the identity matrix. If this one is a 0, then it can't be an identity matrix. And so when you have something like this, whether or not it's on the column or it's on the row, that matrix is singular, all right? It can't have an inverse. So this is just like, like showing that you can't have it, but it doesn't actually tell you how to find the matrix, right? And so that is delved on in a later chapter, but right now we're shown finding the inverse of a 2 by 2 matrix. All right, and so keep this in mind. This is known as the determinant. This is kind of like a sneak peek at something that'll come later on. It's a bit of foreshadowing. But if you have a 2 by 2 matrix with A, B, C, D, to find the inverse, you divide everything by AD minus BC, right? This is the determinant. That's why also it can't equal to 0, because then it'll be 1 over 0. And also you swap the D and the A. So it's like that. And the B and the C are both multiplied by -1, But yeah, it's just that. It's very simple. And here's a bunch of rules. Here are a bunch of rules that have to do with inverse matrices. So if you have the inverse of A times B, that's the same as the inverse of B times the inverse of A. If you have, there's a bit of stuff with powers here. If you A to the power of 0, that's the identity matrix. Similar to any constant to the power of 0 is 1. You have A to the power of a constant. It just repeats that constant amount of times. Negative, what is it? Inverse of A to the power of a constant, the same thing. This also keeps the just general laws of exponents. So A to the power of R times A to the power of S equals to A to the power of R plus S, and A to the power of R to the power of S is same thing as A to the power of RS. Here the inverse of an inverse is just the original matrix. And if you have a matrix, if you have an inverse of like the power, you can just move it around. It's the same thing, If you do A to the power of n and then from there you do an inverse, it's the same thing as doing an inverse like several times, like back like this, And last thing, if you have Ka inverted, not only do you invert the matrix A, but you also invert the constant K. That's pretty important. So, moving on, matrix polynomials. Yeah, so polynomials is just like multiple numbers, right? So you have A, like for example, you have like these A's represent real numbers, and just like the the coefficients of the numbers in the polynomial, and then the x is the variable, and then t is just like as how big it goes. It goes on up to like whenever you want. It's just a random number, right? And then here you can just put in you can just put a into it. You can just put matrix into it, and it kind of works. But instead of like this a0, make sure you put the I there. All right, make sure like each step you have like some matrix, because the matrix does not equal to scalar. All right, important to keep in mind. So let's work through this. Let's say px is x squared minus 2x minus 5, and a is minus 1, 2, 1, 3. Find p a, right? And so starting that off is going to be very simple, right? You have x, so that's just a squared minus 2a minus 5i, right? Let's open that up. So a squared is just, a times a. I'm just going to like speed up the process by trying to do it in my mind. So that's minus 1 minus 1, that's 1. And then that would be plus 2. Doing it here now is minus 2 plus 6. Here now that would be minus 1 plus 3. And then this would be 2 plus 3. Did I get that right? 2 plus, no, 9. Okay, and then the minus 2a is just minus, double this, so that'll be minus 2, 4, 2, 6. And the 5i is just the identity matrix multiplied by 5. Can just put these together. So that's 3, that's 2, that's 4, that's 11, that's yeah, these are the same. We can just put these together actually. That would be okay, since these two are minus already, I think I'll like add on, so that'll be like 3, 4, 2, 11. That goes together, and the result is 0, 0, 0, 0. It's a little bit of a funny thing. Just double checking that is the case. Yeah, okay. Well, that's that. And we're just going to finish it off pretty simply, just properties of transposed matrices. It's just some final things that for some reason weren't referenced in the previous chapter. But if you flip something twice, it's just the original thing. You have a plus b flipped, it's a flip plus b flip. If you have a minus b flipped, it's a flip minus b flip. If you have a constant, it doesn't matter if it's inside, outside. If you have a times b flip, then you actually have to swap it, remember, because it's not, well, I forgot the term, but ab doesn't equal to ba, so this will be b flip, a flip, and then if you have the inverse, it can go in whatever order, which means that if a has an inverse, that means at does also have an inverse. All right, so that's everything. Yeah. Oh god, it's freaking. This always takes so long.